Okay, now we're going to start a new topic, work and energy. So this is PowerPoint 10. Work and energy, they are scalars, as we're going to see. And then they can also help us solve problems which are where the object is not moving with constant acceleration. Because we already learned Newton's second law, Newton's laws, kinematic equations, right? They are very powerful. If you want to solve any the motion of any object in constant acceleration motion, usually you can just use Newton's second law to predict to find the acceleration and plug the acceleration in kinematic equations. You can make predictions about the velocity and distance travels. Right? When the acceleration of an object is not a constant, so the motion can be very complicated. In this case, work and energy, we can make and can help us make predictions in such a case where the kinematic equations and Newton's laws are a little bit hard to apply. So that's the reason we want to study work and energy. And of course, work and energy, especially energy, is also a very important concept in a lot of subjects, not just physics. Okay. So let's take a look at work first. Work has a definition. Okay, everything has a definition in physics. So the definition of work in physics is this: if there's something moving under a force, under external force, and then the force, the object has moved a distance, so we can also calculate work from this force on this object using this definition: force times displacement times cosine theta. So the force obviously is just going to be whatever the forces are on this object. Theta r is the displacement. Okay, that's a symbol we use for the displacement. Cosine theta, what is this theta angle? Okay, you don't really need to memorize what this theta angle is, right? Take a look at this definition, right? You have cosine theta angle multiplied by two vectors, okay? And we're using only the absolute value sign means we only use the magnitude of these two vectors because work we define here is scalar. But these two guys, they are vectors, right? Force has a direction, displacement has a direction. So the theta angle must be the angle between them, right? That's how you make this definition meaningful, right? If you have two vectors and then you multiply them by cosine theta and you tell me theta angle has nothing to do with two vectors, that's a terrible definition, right? So you don't really need to memorize. When you see this definition, right, you will get all these definitions. You don't need to memorize them. When you see this definition, you know what this theta angle is. It must be the angle between the force and the displacement, right? And what is the unit for work? The unit is, if you take a look at the units of these two guys, force and displacement, that must be newtons times meters, right? And we do have a new name for it. We call it joule. Okay, so the SI unit for work is the joule. And then there are some special, let's take a look at some special cases. The simplest case is this: if a force is parallel to the displacement, right? So think about this. If you're pulling something, okay, the simplest case on a surface, you use a force F, pull it to the right, okay? And then if I want you to find the work done by this force, you would just do, and it's going to move in the same direction, like this. And the work done by the force F, because the force is in this direction, the displacement is also in this direction. At the straight line displacement, right? So you would just do force times the displacement times cosine. What is the angle between them? If the force and the displacement are in the same direction, the angle is going to be 0, right? So that's going to be cosine 0, and that's just going to be force times the displacement. That's the simplest case. That's the simplest case, okay? When the force and the displacement make a 0-degree angle when they are in the same direction, you just get force times displacement, right? Okay, that's a very special case. Another special case is this. If there's a force anti-parallel or opposite to the displacement. So in this case, it could be there's a friction on this object, and I want you to calculate the, but it's still, this force is still pulling it in that direction, and friction force is always opposite to the motion. How do you calculate the work done by friction? Well, I would still use the magnitude of the friction force, magnitude of the displacement. Now what is the angle between the displacement and the force, friction? Displacement is still in this direction. Friction is in that direction. The angle between them is not 0 anymore. It's 180, right? What is 180? That's going to be -1. Cosine 180 is -1, so you get negative the force times displacement in this case. So if there is a force opposite to the displacement, you will get a negative number. You see that by this definition, the work done from a force on the object can be negative. Okay, this can be a little bit confusing to people because we use this word work a lot in our life. Okay, so when people talk about negative work in real life, negative work doesn't mean anything in real life. Okay, but this work we use in physics has a definition, and by this definition, the number you calculate can be negative. Okay, so this work has some similarities to the word work we use every day, but they are still, you shouldn't think them as one thing. They're not the same thing, okay? So it helps if you just disconnect them, okay? Forget about how you use this word work in your real life, okay? When you calculate work in physics, all you need to do is just use the definition, calculate work, okay? Don't overthink, don't connect it to your own experience. Don't interpret work using your own definition, okay? If you get a negative number it is, okay? Because by this definition, work can be negative. Now, that's another special case, right? The third special case, let's take a look, say, normal force. If I want to calculate the work done by normal force, what are you going to do? You're going to do magnitude of normal force times displacement times cosine angle. What is the angle between normal force and the displacement if it's still moving in this direction? That's going to be 90 degrees, right? And what is cosine 90? That's 0. So you will get 0. So if there's a force perpendicular to the displacement of the object, it doesn't do work. It doesn't do work, right? That's only because of this definition, okay? I'm not going to remember this special case. There's no point, right? If I have a force parallel to the displacement, I just plug the angle in. I will find out it's going to just be a force times displacement. So there's no point to memorize this. We just want to use these special cases to, again, help us get a little bit more familiar with this work defined in physics. It's different from the word work you use every day, okay? So don't try to interpret this work, okay, using your own definition. Don't compare it with anything you say in real life that is work, okay? Now, take a look at the second slide. I want to use this question again to help you understand the definition of work in physics. So I want you to tell me if a person, okay, is carrying, it's holding a briefcase not moving, or if the person is holding it on a moving walkway in an airport. In each case, is the person doing work on the briefcase? That's the question I want to ask you, okay? So take a look at this question, think about it. What is your answer in each case? Are you doing work on the briefcase if you just hold it, not moving? And if you hold it on a moving walkway in an airport. Now let's take a look at the first case. Are you doing work on the briefcase? Again, I'm not going to try to figure it out using my own understanding of this word, work, okay? Use this definition. Take a look at these three numbers, okay? If the person is holding this briefcase, not moving, so is there a force from the person on the briefcase? Yes, right? And of course, the force from the person is going to be straight up because it's going to balance gravity. So if you want me to figure out if this person is doing work on the briefcase, I just need to multiply this number by the displacement and the cosine theta angle. That's it. I'm not going to overthink. I'm not going to use my own definition of work in my life to figure out. Okay? What is the displacement in this case? There's no displacement. If there's no displacement, there is no work. There is no work. So in the first case, when you're holding a briefcase, not moving, you're not doing any work on the briefcase. Okay? And people may say, well, okay, say if the briefcase is really heavy, I feel really tired doing that. How come I'm not doing work? Again, you can say that if that's how you want to use work in your life. Okay? You can use a word in any way you like. You can use a word even different the way people use that word, right? But everything in physics has a definition. We have to call it a name. In this case, we decided that what's important is this concept. This concept is very important in physics. But we want to call it something, right? We don't want to say force times displacement times cosine theta all the time because it sounds funny. And because this thing we define, it's a little bit similar to the word work we use every day. So why don't we call it work? Okay? So we don't need to make a new name for it. Okay? We don't need to make a new name for it. Okay? But whenever you calculate work in physics, you use this definition. You don't use your own definition, right? We don't define work as how tired you are, how hard this thing is, right? Now, the first case, no work. What about the second case? You hold it on a moving walkway. The freeboard diagram is still going to be this, right? Because the moving walkway in an airport, it's moving at almost a constant velocity. If it's moving at a constant velocity, the net force on the briefcase must be 0. If the net force in the briefcase is 0, the force from the person must be straight up, right? Cannot have a component that way. A lot of people, they would draw the force in this direction. No. If you draw force in that direction, it will be accelerating. That's Newton's second law, right? You can't violate Newton's laws, okay, in your life, okay, in macroscopic scale. So if you want to figure out the force from the person on the briefcase, it must be straight up. Okay, in order to obey Newton's laws. So in this case, the force is going to be equal to gravity. Okay, so I will get a number if I want to calculate the work. Is the briefcase moving in this case? Yes, because it's moving with the person and the walkway. So there will be a displacement in this direction. I will have a number for the force. I have a number for displacement. What is the angle between them? In this case, angle is 90 degrees, okay? You put these three numbers together, but you will get a cosine 90. Cosine 90 is 0. You don't need to calculate anything. You're not doing work to the briefcase in the second case, okay? So in both cases, the work from the person on the briefcase is 0, okay? It doesn't matter how tired you feel. It doesn't matter how hard this thing is to you, right? Even if you are you carry 2 weights in the gym, okay? It's really, really hard. You're using very heavy weights. If you're not moving, there's still no work, okay? You're not doing work by this definition, okay? Let's take a look at the next one, okay? The question on slide 3. So this is an interesting one. So now in this case, I still want you to tell me if the person is doing work on the briefcase when the person is on an escalator carrying a briefcase and the briefcase are moving with this escalator, again at a constant velocity, right? These escalators, they usually move at a constant velocity. So what is your answer in this case? Are you doing work on the briefcase? Is the person doing work on the briefcase? in this case, when he's not on a moving walkway, he's on an escalator, which has an angle with the horizontal, right? So what is your answer? Think about it. What is your answer? Yes or no? The answer is yes. Okay. Why? Let's still find these three numbers, right? If I have 1, 0, then it's going to be 0. If I have three numbers non-zero, then I will get a work at the end. Now let's figure it out. First of all, how do you draw the force from the person on the briefcase? Still straight up, right? When they're already moving, when the person and the briefcase, they're already moving on the escalator, they already have the velocity, so the force from the person must be drew straight up. The person cannot have a force in this direction, otherwise the briefcase is going to be accelerating, which is not the case here. So from Newton's laws, the force from the person is still going to be straight up on this briefcase. Some people feel it's weird, right? How does the briefcase start to move in the first place? That's a different process, okay? So you should split it up. When the person steps onto the escalator, at that very second, he will have a force in this briefcase in that direction in order to start this briefcase in motion, right? Because in that very short amount of time, the velocity of the briefcase is going to start from 0 to some value, to the speed of the escalator. And that's going to be a very short process, right? You step on the escalator, then that's it, you're going to move with the escalator. But in the first process, this very, very short process, you will have a force on this briefcase in that direction in order to accelerate it from 0 to the velocity of the escalator. That's the first process, right? Once you have finished that process, you're already on the escalator, you're not going to have any force in that direction. You will just have a force straight up on the briefcase. Okay, everything's changing. Everything's changing. The force from you on the briefcase is also changing in these two different processes. Okay, you shouldn't just assume the force is constant. There's no change, right? There are two different processes. There's the first process, really quick. You step on the escalator. In that process, the briefcase is accelerating. Okay, for a very short amount of time. But after you are already on the escalator, everything is going to be a constant, so the force from you on the briefcase must be straight up so that all the forces cancel out on the briefcase, no net force. The briefcase will be moving with the constant velocity. Okay? So that's the force. Is there any displacement for the briefcase? In this case, yes, because the briefcase is moving with the escalator, right? So the briefcase is moving this way. So you will have a displacement. It will have a displacement. So that's the displacement. Okay, so I will have two numbers. I don't need to plug them in. I just want to find out if I'm going to get a number or 0 at the end. Is there angle cosine theta you should plug in? Yes, I will get an angle. Is this angle cosine 90? Because only 90 degrees is going to give me a 0. This angle is not 90. They don't make a 90-degree angle. So in this case, you will have three numbers, non-zero. You multiply them together, you will get a number. So in this case, the person is doing work to the briefcase. Okay? So, and again, a lot of people feel it's weird, right? Compare this with the walkway. If I'm the person, I don't really feel any difference. Right? I'm just standing there. How come that on the walkway, I'm not doing work on the briefcase? I'm on this escalator, I'm doing work to the briefcase. That's only because of this definition. Has nothing to do with your feelings. We don't define human feelings in physics. We don't define anything based on how a person feels in this process. If a person feels differently, the number is going to be different. If the person feels the same, the number is the same. Forget about your feelings. Forget about your senses. Okay? We don't use our senses in physics. We don't use our intuition, in physics, right? We define things, we do math, we get the right answer. That's it. Okay? So I want to use these two questions to help you understand this definition. Always use this definition Doesn't matter it's a work or speed or anything, right? For example, if I ask you the velocity of this, the direction of this velocity when the person is on the move walkway and then the escalator, you would say, I still don't feel any difference, but the direction of velocity has a definition, right? When you're on the escalator, it's in this direction. When you are on the move walkways in this direction. So if I want to compare these two velocities defined in physics, I would say they don't have the same velocity. Only because the definition, right? I don't care what you feel, I don't, right? Physics doesn't care how people feel, right? We don't study human behavior in physics, human feelings in physics. We study nature, right? We define something, we just use the definition, do the math. That's it, okay? Okay? And some of the things in physics, they are even counterintuitive. That's why we don't always trust our intuition. We don't always use our judgment, our own definition, our own feelings, our own understanding in physics. We don't. We trust math. We always do math, okay? All right, so that's that. Now, strictly speaking, the definition of work is actually a dot product between the force and the displacement as vectors, because we know that the force and displacement, they are vectors, right? So the former definition of work is actually the force starting to the displacement. And then if you remember the definition of dot product, okay, if you have two vectors in a dot product, you will just get the magnitude of the product of these two magnitudes multiplied by the angle, cosine theta angle between them, right? So this is the definition of a scalar product or dot product of two vectors. So actually mathematicians, they define all these tools even before physicists adopted their tools, okay, in physics, okay? Mathematicians, they define a lot of things, okay? They define a lot of things, okay? Even if like you can't find everyday equivalent, they will define that, they will make a theory out of it. Some of the theories, physicists just realize they are useful. These tools are very, very useful in physics. So we're just gonna use their definition, use the tool mathematicians invented. We can use these tools, use these definitions in physics, okay? So strictly speaking, work is a scalar product, a dot product between these two vectors, but that's just a nicer way to write this definition, right? If you like, you can still just use this definition. The work is always force times displacement times cosine theta, okay? And then for a scalar product, if you still remember, if you want to multiply two vectors, the easiest way to do that is to use components, right? So all you need to do is just multiply x components, multiply y components, and z components, and then add these three numbers you get, okay? So that's how we do dot product with the component form. And then there's a commutative law and distributive law for dot products, and then which are intuitive to us, because you can just treat them as numbers when you multiply them in dot product, right? Okay? So that's the definition of work for a force which is a constant. If there's a force which is not a constant, right, which is actually very common in real life, we usually start with like constant force, velocity, acceleration in physics, but they are actually simplified, right? In real life, everything is changing, okay? If you want to define work for varying force, okay, for changing force, you can still do that. The definition just becomes an integral, okay? So the work definition, the more general definition of work for any force is actually this. Okay, you just integrate the force over the displacement from initial point to a final point. Then you can calculate the work done by the force and this displacement. Okay, that's the definition. And if you make a plot, if you have the force in x direction, you make a plot of the force versus the position. Actually, the work is just going to be equal to the area under this force curve, right? That's something you learn in calculus. But in this class, because it's an intro-level class, we're just going to be working with constant force, right? We're not going to really work with a varying force in this class, but that's just going to be, that's the general definition for work. Now I want you to use this definition to calculate work in a real process with some numbers. So take a look at the question on slide 7. Suppose a force of 10 newtons is applied on a 2 kilogram box at rest on a frictionless surface. Find the work the force does on the box in 3 seconds. Okay, if I want to find the work done from a force on an object, all I need to do is just use the definition. Find the force, find the displacement, find the angle between them, multiply these 3 numbers together. That's it. I don't need to use my own definition. Use my own understanding or my own judgment. Do I know the force? Yes. I want to find the work done by the force 10 Newton on this object. Okay, I do have the force. The force is going to be 10 newtons. Do I know the displacement? I don't. So that's something I need to find before I use this definition work to find this work. Do I know the angle? Let's take a look at it. I'm going to draw this force and the displacement. So in this case, this is the simplest case, right? A force is applied to an object and it's going to rest on the frictionless surface. So if there's no friction, then this object is going to move in the direction of the force. So after some time, the object is going to be here. So the displacement and force are in the same direction, right? So in this case, the theta angle is going to be 0. I plug in. So the only thing I need is the displacement. How do I find the displacement? Well, this is a constant force, constant acceleration motion. So you can use the kinematic equations to find the displacement. If I want to find the displacement, I need the acceleration. And acceleration, you can find it using Newton's second law, because acceleration equals net force over mass. Once you find acceleration, you can pick one of the kinematic equations to find the distance it travels. And because we know time, and we also know the box initially at rest, so the best equation is going to be the second kinematic equation. Okay, so that's what we're going to do. Use Newton's second law to find acceleration of this guy, and obviously it's going to be in x direction because it's not moving at y direction. And use that acceleration, plug it into the second kinematic equation, find the displacement, then use the definition work to find the work. Now you can pause the video, finish the algebra. All right, let's see. The acceleration in x direction, it's going to be the net force in x direction. No, I'm going to do it here. Divided by mass, right? So there is a force down, gravity, normal force out, but I know these two forces, they're going to cancel out. So the only force, if there's no friction, it's going to be the 10 Newton force, right? And the mass of the problem says the mass is 2 kilograms. So this is going to give me 5 meters per second squared. So that's acceleration. Then I can go ahead and use the second kinematic equation. This is xf, right? This is xi equals 0. You can assume this is your origin. xf equals xi plus vxi delta t plus 1/2 ax delta t squared, right? And then you plug all the numbers in. This is 0, this is 0, and then you already have the acceleration. No, there's no a net. This is just ax. I'm sorry. And the time, what is the time? Time is 3 seconds, right? So this is 3 seconds. So you plug all the numbers in, you will get the displacement. It's gonna be 2.5 meters. Now you can go ahead and use the definition work, right? The force, the displacement, the cosine theta, you will get, what is the number you get? 225 joules. So that's the work done by the force. Okay, so the force is doing work on this object. So where did this work go, right? So the force is keeps doing work to the object. Where did this work go? What is the change of this object? Is there any change on this object? Well, I know that the object is going to get faster and faster, right? But where did this work go? I have to define something. So our theory in physics, we have to define a consistent and complete theory. So the work and energy theory in physics is this. So in this case, the work has been converted to the energy of this object. And this energy is connected to the motion of this object. So we call it kinetic energy. And what is the definition of kinetic energy? Take a look at the next slide. The definition of kinetic energy is this. We use a symbol K usually for kinetic energy, and the definition is 1/2 mv squared. And this unit is going to be kilograms times meter per second, and this unit squared, right? And you can show that this is going to be equivalent to Newton times meter, and Newton times meter is joule, right? So the SI unit for kinetic energy is still going to be joule, okay? And why do we define kinetic energy this way? Actually, the first time I learned kinetic energy, this definition was really weird to me, right? 1/2, and that's v squared. That doesn't look like really intuitive to me, right? Let's use the next question, the question on slide 9, so we can see why you need to define kinetic energy that way. Because you can only make a consistent complete theory using that definition. If you define kinetic energy in a different way, you cannot make a complete or consistent theory. So let's see. Now in this case, I want you to do this in this question. I want you to use the definition of kinetic energy. Find the kinetic energy of the box at this point. So let's call it K final. How do I find the K final for the box at this point? Well, use the definition of kinetic energy. I would just do 1/2 times mass of the box, which is given 2 kilograms, right? Times VF at that point. How do you find VF at that point? I can just use the kinematic equations, right? Because this is a constant acceleration motion. So if I already know the acceleration and the time, so the best equation is gonna be the first equation, the simplest one. And you use that equation, you can find the final velocity. And once you have the final velocity, you can go ahead and find the kinetic energy. Okay, pause the video, do the algebra. Let's first find the kinetic final velocity. That's just gonna be Vxi plus Ax delta t, right? Vxi is 0, so you only have Ax delta t. We already have Ax 5 meters per second squared, delta t 3 seconds. Now this is going to be 15 meters per second. Now let's do this. K final 1/2 mv x final squared. You put all the numbers in, what do you get? You get 225 joules. All right, you see that this number equals that number. So why do we define kinetic energy in this way? If I ask you, what is the initial kinetic energy of the object when it's at rest? Well, that's going to be 0, right? Because at rest, then the initial velocity is 0. So in this process, if you define kinetic energy this way, you can see that all the work has been converted to kinetic energy of this object, 100%. So in this case, you can say the work has been converted to the energy of this object. And in this case, is the kinetic energy of this box. So that's why you define kinetic energy this way. And you can actually show that. If you do the math, you can show that this is the only way you can derive this definition of kinetic energy if you want the work to be converted to the kinetic energy of this object 100%. Right? But we just use this definition. We're not going to really derive that. So that's the definition of kinetic energy. Right? Now let's take a look at another question, slide 10. I want you to find the work in this case for me. A 2 kilogram block slides on a rough surface for 2 meters before it stops. So it has some initial velocity and it's sliding on the surface. Of course, the surface, a real surface, is going to have friction force on it. It's going to slide 2 meters before it stops. The coefficient of kinetic friction force is 0.3. What is the work done by the friction force? So I'm calculating work done by a certain force. All I need to do is just use the definition of the force, or definition of work. Find the force, find the displacement, find the cosine theta angle, multiply them together. Now I want to find the work done by the friction force, so the force I plug in is going to be friction force. How do I calculate friction force? We do have a theory for kinetic friction force, right? The theory is that the kinetic friction force is equal to mu k times normal force. And mu k, the problem already gives us, the mu k is the 0.3, right? That's why. So that's how I'm going to find the kinetic friction force. Normal force in this case, well, this is the simplest case. You have a block on a rough surface, horizontal, gravity is down, normal force is up. So in this case, and friction is in that direction. It's moving in this direction, and at the end it's going to stop. So in this case, normal force will be equal to gravity, right? Straight up. Now you can go ahead and then find the kinetic friction force. And then, what is the displacement? It says it's going to slide 2 meters before it stops. So the displacement, the problem already said, that's just going to be 2 meters. What is the angle between them? Well, you should be careful, right? Displacement in that direction, friction force in this direction, what is the angle between them? That's 180, that's not 0. You should plug in 180, not 0. All right, so that's going to be all the numbers you need. You find the friction force, multiply the force, displacement, cosine theta angle. You should get the work. Okay, pause the video, find the work. So the kinetic friction force, if you plug in normal force equals gravity, right? In this case, you will get the mass, because the mass is 2 kilograms. You will get 5.88 newtons. And then you use the definition of work, right? The work done by the friction force, kinetic friction force. It's going to be friction force, displacement, cosine 180. You will get a negative number. All right. So negative materials, don't make it positive. As I said, by this definition, the work you calculate in physics can be negative. What does negative mean, right? What does negative work mean? I don't really understand what negative work is in my life. Again, don't connect this thing to the work you use in your own life. Don't use your own understanding. Everything has a definition in physics. We just give it a name, work. We can call it different names, right? It's not going to change the definition. What does negative work mean? Think about this. What is the final kinetic energy of this object? Well, I don't need to calculate that because it stops at the end, right? So the V equals 0, so that's going to be 0. What is the initial kinetic energy of this object? Well, that's going to be some number I can calculate. 1/2 V initial squared. 1/2 mv initial squared. Well, I don't have this, but I can calculate this initial speed. I'm not going to do that here, but I know kinetic energy is going to be some number greater than 0. So in this whole process, you see that the kinetic energy actually, from the initial kinetic energy to the final kinetic energy, the kinetic energy actually goes down. So it's losing kinetic energy because initially it has some value. At the end it has 0. And you can actually calculate the initial kinetic energy. The initial kinetic energy is just going to be 11.76 joules. So you see the energy is going to change from 11.76 to 0. The negative work just means it's taking energy away from this object. Okay, it's going to lose 11.76 joule of energy. All this energy has been taken away from by the friction force. That's what negative work means. You see that the theory is complete and consistent. The negative work just means some force is taking energy away from this object. So we have made a complete and consistent theory by this and this definition, right? Okay, so don't be afraid of negative work. If you have an angle larger than 90 degrees, you will get a negative number because cosine theta will be negative. So you get a negative work, you leave it there. That just means the object is losing energy. Some force is taking energy away from this object. Okay, so that's that. That's negative work. So don't ever be afraid by negative work. Now I want you to take a look at the question on slide 12. How much work does an elevator motor do to lift a 1500 kilogram elevator a height of 60 meters at constant velocity? I still want you to calculate work. Now in this case, the work done by the motor on an elevator. Okay, you want me to calculate work, I'm just gonna use the definition of work again. So let's find the force, displacement, cosine theta. So if this is the elevator, so it has gravity, right? And then the motor has a force on it. Let's call it F motor. So I'm calculating work done by this guy. That's the problem it wants me to calculate, right? How much work does the elevator motor do to lift this elevator? So the work done by the motor is going to be the force of the motor times displacement times cosine theta. So the displacement, the problem already tells us, the motor is going to lift the elevator a height of 60 meters, right? So it's just going to move up 60 meters. So that's the displacement, right? And then what is the angle? So I know this time. What is the angle between the force and the displacement? In this case, that's the simplest case. Again, the angle is 0. Because the force and the displacement, they are in the same direction. So the angle is 0. So I know this. But I don't know the force of the motor, right? Let's read this question a little bit more careful. It's lifting the elevator at a constant velocity, okay? So I see constant velocity. These two keywords implies that the net force on this object must be 0. That's Newton's first law or second law. If the net force on this object is 0, so I know that the force from the motor must be equal to gravity. So the problem doesn't tell me the force of the motor directly, but I know it's going to be equal to the gravity of this elevator. So I can calculate this number and then equal that, right? So, but remember, we're not calculating work done by gravity in this case, right? We're still calculating the work done by the motor force. That's why the angle is going to be 0. If you want to calculate work done by gravity, you get 180, okay? So, but it's only because this number equals that number. So I can replace this number with this number. Now you can use all the numbers and calculate the work done from the elevator motor to this elevator. All right, what is your answer? The answer I got is, it's a very large number, 882,000 joules. So that's the work done from the elevator motor on this elevator, right? Now, I still want to ask you this question. So the motor is doing work, to the elevator. Where did the work go? In the previous case, with this block moving, we know that the work is just going to change the velocity, the kinetic energy of this object. If the work is positive, so it's just going to become the kinetic energy. If the work is negative, it's just going to take kinetic energy away from this object. In this case, it's the motor is doing work to this elevator, but take a look at the kinetic energy. Is this kinetic energy of this elevator changing in this process? Of course it's not, because the problem says it's moving at a constant velocity. And constant velocity, that means V stays the same. If V stays the same, K, this definition, by definition, kinetic energy is going to stay the same. So in this case, kinetic energy is not changing. So the work is not being converted to the kinetic energy. Where did it go? Again, you have to make this theory complete and consistent. So that's why we need to define another type of energy which is associated to gravity. We call it gravitational potential energy. The reason you need to do some work to lift this elevator is because of gravity. So I have to define another thing associated with gravity, another energy. So in this case, the energy, the work, is going to be converted to that energy associated with gravity, right? And that energy, we call it gravitational potential energy, and the definition is going to be mgh. And again, you can show that the definition of this, the unit of this is kilograms times meters per second squared, which is the unit of little g, and times meters. And this is going to be equal to this, right? Because this is going to become meter squared divided by second squared times kilograms. And then this is going to be equal to newtons times meters and then joules. So all energies and work, they have the same unit. That's why they are connected. In this case, you see that, and why do we define it this way? And you see this theta r is just going to be the height in this process. So by defining gravitational energy this way, you can see that all this work has been converted to the kinetic energy of this elevator. So complete and consistent. So potential energy, we can, it's a very special type of energy. You can only define potential energy for conservative force. So gravity is a conservative force, and then there's another type of conservative force, which is the elastic potential energy. We're going to discuss that next time. So I'm going to stop here for this video.